Hello, everyone. So welcome. This is a talk at MassRobotics, and we have a number of speakers this afternoon. The first person we're going to have talk is Tom Ryden. He is the executive director. Joyce is going to talk. All right, and tell you a little bit about MassRobotics.
Welcome to MassRobotics. We are a shared workspace for robotics companies. We opened up in about February. We had a grand opening. We have actually been an organization for a couple of years now, and everything came together this year. We currently have 12 companies in our space, and our resources include a machine shop we're working on, some 3D printers, we have an electrical lab, we have some private offices, some shared space that you're in, some conference rooms, and private labs and private desks or private benches. Our mission is really bringing together the community and the robotics startups and giving them the resources they need to further their companies. Robotics is a very large growing industry. Just recently, VCs have really started putting their money into this area. There's a long return on investment with robotics, and I think they're realizing that this is really the trend of the future. We have several founding sponsors in order to get us started in this space. We have 10 companies who put their resources into us and believed in us. We also have sponsors that are annual sponsors. Some of the other things that we provide our companies here are software from some of our sponsors. So the MathWorks, SolidWorks, Autodesk, and Amazon Web Services all provide resources for the companies that are in the space. We have 5 founders and an executive team and a terrific board of directors. You'll probably recognize a lot of the names on there. Another thing about our space, so we started with this 15,000 square feet that we're in now. We also have the opportunity to build out 25,000 square feet on the second floor. So in order to do that, we're running a big capital campaign to raise the funds to be able to do that, that build out. So the name MassRobotics came about, one, because we did start in Massachusetts, but basically it's robotics in the masses. Robotics is really happening around the world. And so we are connected to a lot of those other countries. So we have had in our space the French, the Chinese, the Japanese, the Koreans, people from Singapore, the Netherlands, the UK. We also work with several universities, partnering in many areas, helping their startups, having their professors sit here. We're working with co-op students for Northeastern. Again, these are our international engagements. And we also run several events to bring the community together, everything from our monthly meetups to our lunch and learns that are a little bit more technical to social events. And for more information or to become a partner or a resident, you can contact us. You said 5 minutes.
Well, thank you very much. So our next speaker is Michael Misha-Novitsky. He's a researcher at MIT on the Aquaticus program. He's going to talk to you about that. Let's see,
Great. So hi, everyone. I'm Michael Novitsky. I'm a postdoc at MIT in the Mechanical and Ocean Engineering department. I'll be presenting today on Aquaticus, a mixed human-machine robotic competition. So a little bit about myself. I go by my Russian nickname, Misha. I originally started in psychology with my undergraduate degree in 2003, and then took some time off to go work. And while I was doing that, I thought, let's go try to get a PhD in child development. And as I was waiting to hear back from the schools after my application was in, I bumped into some friends from the Air Force while at the gym, and they were completely mad about these things called drones. Drones were getting in their airspace, drones were trying to land while they were trying to land, and they were like, Misha, that would be something cool that you should go check it out. Once I went to go check it out, I completely changed my trajectory, started learning computer science and engineering, ending up at Georgia Tech. I got my computer science degree in 2009, and then electrical engineering in 2014 with my PhD in robotics in 2015. So I saw earlier while going through the MassRobotics website that one of my good friends, Liam Paul, gave a presentation on Ducky Town, which is why I'm wearing my ducky tie. What it was, Ducky Town was a class on autonomous cars taught to students, and it was spearheaded by Andrea Censi and Liam Paul. And what they did was recruit a whole bunch of postdocs just like me, maybe around 20 of us, to put the class together, then recruited around 22 to 26 students to actually take the class. It was pretty fantastic. The postdocs, as a group of postdocs, we put together the software for the class and the hardware. So when the students showed up, they started putting everything together and building off of that. And this is actually the pinnacle of the class. We did a large demonstration for MIT Open House. They estimate around 30,000 people came through the ice rink where we were. It was a great opportunity. I got to meet a lot of great people at MIT. It was a lot of fun. But one of my favorite people I met was Baby Gus. And Baby Gus is the child of Liam Paul, one of the youngest. We spent a lot of time together, especially getting ready for the demo, as you can see, was really important. All right, so a little bit of background about the lab where I'm working at, and then we'll go through some of the projects, talk more about Aquaticus, how we actually interact with the robots that we're going to be using, and then some experiments, followed by the actual capture the flag competition, challenges, and some next steps. So I'm part of the Laboratory for Autonomous Marine Sensing Systems of the Mechanical Engineering Department, headed by Professor Henrik Schmidt, and I work closely with Michael Benjamin. So the specialty of the group is marine autonomy. We do a lot of ocean environmental acoustics, modeling and simulation. And particularly, they're doing a lot of autonomous and adaptive collaborative acoustic sensing and undersea communication. And this picture that you're looking at here is actually from 2005 in Italy, where they were launching the 21-inch AUVs and some autonomous surface vehicles. I have yet to go on one of these trips, but I hear they're a lot of fun. Here is a great video of one of the last experiments that they went to do. So what they're doing is looking at differences in the Arctic environment. So as the Arctic is changing, they're finding that the acoustic signature is different. And this is important for a lot of different people, including for environmental monitoring and communications in the water. If I can get this video to play. Do we have audio coming from the laptop? Oh, we do. Great. So the audio for this has nothing to do with the video. Can I lower the volume? Great, so there you see one of the vehicles. They're putting it underwater. On the right side, you're actually seeing a GoPro that's attached to the underwater vehicle. And as it's going through, now this is of course sped up because it moves way, way slower because they're trying to make sure that they're accurate in their tracking. Our supervisor, Mike Benjamin, really enjoys music in the videos. As you can see, it's quite gorgeous. And they found some very drastic changes in the Arctic Ocean. This is at the Beaufort Sea, and they're trying to track exactly how well they can do monitoring. So we actually have a laboratory under LAMS at the MIT Sailing Pavilion. It's a really, really great place. From the pavilion, you can see here there are some wooden docks. That was actually the original dock structure, and everything was packed. They would take boats and put them all inside of the little sailing pavilion. As they got bigger, they expanded to the gray dock, which is a floating dock, and they started bringing boats out, which allowed us to actually take one of the high bays, which is on the furthest right there, and start using that for our own base of operations. So prior to them actually doing that, they had to lug their robots down to the pavilion from across campus, which of course takes a lot of time, a lot of energy, and if things don't work really well, then you're just sitting on the dock with a bunch of equipment that you have to take back later. Out of the pavilion lab, we do a lot of education and research in particular for autonomous marine systems. So the highlight of our education experience here is teaching the course 2680. It is the Unmanned Marine Vehicle Autonomy Sensing Communications course. Here is a picture we took, I think, like last week. Yeah, class just ended last week. It was pretty awesome. They used little ClearPath unmanned surface vessels, and it's a lot of fun. So a lot of work because they're learning about programming, they're learning about using our software infrastructure, and then trying to get on the water, trying to do the projects. So a little bit about the software infrastructure of the lab and all the projects that we'll discuss shortly. We leverage software called Moose IVP. So Moose is the middleware that allows all the different interconnections between the software modules. And IVP is the thesis of our supervisor, Mike Benjamin, which does interval programming over objective functions to find the most optimal way to do something. So in general, Moose IVP is designed around using code reuse and allowing you to have your own private repos. So if you think about the center of the circle there, you have the core modules, which is the Moose database, allows you to talk back and forth between modules. And then as you go out, you have the basic autonomy infrastructure, which we have quite a bit of because they've been doing it for at least 15 years. And then on the outsides are if you want to have your own private repos, which we certainly have projects that do that. So if you are running a Moose community, you have a centralized database called the Moose database, and you have several different nodes that are talking to it, and that's how they share information. It's different from ROS because ROS has a centralized place where you look up who has data, and then you start talking back and forth. But it is a middleware, and at some point, we just end up doing a lot of different middleware work. So in particular for our group, the IVP Helm is important. As I discussed, it's Mike Benjamin's thesis work, and it sets up a hierarchical structure for different modes. So you switch in different modes based on what you're doing. It's a behavior-based system. And for each mode, you have an associated set of different behaviors. So one behavior, of course, can be go to waypoint. Another behavior can be collision avoidance, and you can stack up all the different behaviors. Then there's a solver that takes in all the behavior outputs and gives you a selection of, in our case, speed and heading. One of the things that we leverage quite a bit and came before my time is the front seat, back seat architecture, and we're going to use that and see that quite a bit. Originally, what used to happen is the vehicle would show up, and it was a proprietary system. So if you wanted to put autonomy on there, and you wanted to install packages or fidget with something, then everyone was like, I don't know, if you do that, things might break, so we're not going to let you touch things, which became kind of restraining. So what they ended up doing was separate and say, okay, the front seat takes care of interfacing with the robot and all the hardware, and then we're going to have our own little backseat computer that we plug in this case, through Ethernet, and we can play all we want. We can sandbox, we can add different libraries as we wish, and tinker all we want, and then go from there. It also allows us to hot swap brains as much as we want, which is pretty great. All right, so let's talk about some of the projects that our laboratory supports. The first one here is COLREGs. So if people aren't aware, COLREGs are essentially the rules of the road for the waterway. So just like people do go through where you're at a four-way intersection, what are the rules? I think it's pass on right, person on the right side goes first. Yeah, I haven't driven in a long time. So we're actually doing that for the waterway. And that has to do a lot with the geometry of the vehicles, the size of the vehicle, et cetera. So here, we're showing work by Kyle Warner. And so one of the things we end up doing, because there's a lot of traffic on the river on a regular basis, it tends to get really chaotic. We are doing experiments with about 6 different robots in a very small confined area. We're essentially trying to make them collide. So if you imagine sailboats and other boats coming in the way, it becomes very hectic. So we like testing in the evening so that we can actually make sure that we're worrying about the robots and about nothing else. So here you see about 6 vehicles working back and forth, trying to see if they collide. If they collide, that's very sad. And then we have to go back and work on algorithms. And if they don't, then we keep going. We had many, many hours of testing in this fashion. Our goal ultimately for this work is to have a vehicle not just travel around the world, but also be from one point of a busy harbor to the other, transporting goods, all following the rules of the road. One of the other groups in the lab is Sea Grant. and they have a vehicle here called the WAM-V that they've outfitted. They originally used this vehicle for the Robot X competition. If you're not familiar with that, it was designed to see if people could put autonomy to do different little tasks on a vehicle of this size. They've since transitioned this from the competition to measuring salinity and ocean acidification. The other project we have involving this vehicle is the Boston Harbor Robo Challenge, and the goal for this challenge is to have the robot start from the pavilion, go through the locks, and end up at Deer Island on the other side, here on the image. This is a very difficult challenge. Of course, we have to worry about collision avoidance, which we already talked about in core regs, but then there's also the perception side of the house, which will be difficult, and then interfacing with the humans, because right now it's humans who are at the lock operators, and communicating with them is either over beeps or calling on the radio. So it's all going to be very exciting to get that to work. So let's now talk about Aquaticus. And please feel free to ask questions if I skip anything too quickly. All right, so what is Aquaticus? Aquaticus is a competition where we're putting humans and robots in the same environment. In this case, the humans are in their own vehicle, which is a motorized kayak, with robot teammates that are also vehicles in the water. So we're actually looking at teaming together while they're in the same environment, which is different from other groups that are actually having humans outside of the environment, so in the environment but not actually equal actors in the sense of actually being in a vehicle. We're looking at the trifecta of the intersection between robot autonomy, human-robot trust, and cognitive operator load. And we find that to be a very exciting trade space. So the hypothesis of our group right now is that the effective robot will have a high autonomy capability, and of course, we can always argue what that means, and then high operator trust and the low operator load. So what's the context for all of the different research that we're doing? So there's a couple of projects that highlight what's going on, the bigger picture. So there's the Army MUM-T program, in which manned Apache works with unmanned vehicles, the Shadows. And what they have the gunner do in this case is be able to control the drone by clicking on things inside the screen. So what that gives them is a reach capability. So for example, the helicopter can stay in an area relatively safe, and then send out a Shadow out to get some information. Then when the information is retrieved, then the Apache can do different maneuvers. Then there's another project called the Air Force Loyal Wingman Project. And the Air Force is hoping to get F-35 pilots flying their own jets, but also teaming up with F-16s that are autonomous. So getting rid of the humans and putting them all together. And they're hoping by 2020 to have a good human-robot team moving together. So that's the context for which we're doing everything. So we're MIT. And we're great because we have a lot of intelligent people that we can draw from to help do experiments. We turn our experiments into a game because it's fun and exciting to draw as many people as we can. We think that doing testing on the water is much more accessible, so we don't need fighter pilots, we don't need jets, which are pretty difficult. We certainly don't need clearance from anyone as of yet to be deploying robots on water, and that's pretty great. So, and of course the large population of people. So we've decided to use Capture the Flag as a game that's relatively useful here in the US because a lot of people play it, and it's accessible. So if you've forgotten what Capture the Flag is, I'll give you a quick primer. So we take a field, we divide it in half, and the objective of the game is to go over to the opposing team's field, grab a flag, and bring it back to your flag areas as quickly as possible. The way you can defend your flag, if the opposing team is on your side of the field, you can of course tag them, which makes them go back to their home base to get untagged. If the opposing team has a flag and you tag them, the flag gets returned home and they still have to go and untag themselves. We are trying to do as many flags captured in 10 minutes, and of course that time can vary. We used to think that we would do just one flag capture, but our initial experiments definitely demonstrated that there's a lot going on, and 10 minutes is a great way to do it. So our objectives are to look at the human understanding and trust of robot actions. In particular, we'll talk about this a little later, How do you authorize actions? Who's responsible for that? Does a robot take initiative by itself and then you just consent? Or does a robot do something and then you interject? Or is everything just step by step from the human? Also, what we're looking at is human-robot information exchange. We're already seeing that some of the operators are getting overwhelmed by the amount of data that's coming in. We have different ears with different information, and that's quite a bit to process. And then we want to see how can one human, of course, become a force multiplier with many robots at one time. So let's talk a little bit about the vehicle that the human is inside of. So if you haven't had a chance to come by our pavilion and try this out, you totally should, because it's a lot of fun. It is a motorized kayak by Mokai. You control it by sitting inside of it. It has a little joystick, and you toggle around. Forward, of course, is for going for speed, and then left and right for your angle. It comes with a Subaru engine in the back. It's pretty loud, but a lot of fun. If you're light, it goes about 21 miles per hour. For me, it's a little slower. And what we've done is we augmented it, right? So in order to make it a node on our network so that the robots can communicate and identify where its location is, we've added a GPS, a compass, and a laptop to do the speech recognition, which we'll talk about in a little bit, and then all the other processing that happens on board. Of course, the really large Wi-Fi antenna helps a lot so we can communicate. So this is a great video. This is one of our undergraduates from this past summer. He really enjoyed being on the water. And unfortunately, this video doesn't really tell you how loud the vehicle is, but just it's really loud. Like, it's really loud. You can see that we have put on a headset. We got that from Rugged Radios. It's designed for, I think, rally cars in particular out in California. He has a little blue radio there, which we use to talk to the headquarters. And then he has another button in order to use speech recognition. So he pushes the button, says a command, and that goes to speech recognition. You can't really see it very well in this video, but his entire body is like soaked, and there's little spray coming up. So depending on your speed and the wind for that day, it can be a very wet experience. So let's talk about our autonomous teammates. So these are herons from ClearPath. So ClearPath's in Canada. We get these robots from them, and they've been upgraded tremendously over the previous version. It now goes 2 meters a second, which is actually still a fraction of how fast the Mokais go. So in this case, our human-operated vehicle is super fast, and we're going to find ways to mitigate that. And they now have upgraded to having an electronics box that's removable. So if something goes wrong, you just grab the whole box, ship it away, and replace it as you need to. The one thing we certainly added because of the different testing we're doing, including Colregs and the human robot work, is a giant e-stop. I think we might call it the MIT e-stop, since I think we're the only ones that have it. Super useful for many reasons that we will just keep quiet for now. All right, so we discussed earlier about the front seat, back seat architecture. We have here one of our backseat brains that we put into the herons, and it is a Pablo box designed within our lab, and it actually just runs with a small $35 Raspberry Pi, right? So we take all of our autonomy, all the thinking, all the Colregs, and thinking about the collisions in our contacts, and put them into this little Raspberry Pi going forward. It's really crucial to note that we are not doing perception with this Raspberry Pi, because they can get overwhelmed pretty quickly. This is strictly just the autonomy. It's great for students because they can take the box with them home. They can play with the sandbox and then come to class, put it in, and get going. For us, it's great because also in the Aquaticus project, we're hoping that teams will show up with their own autonomy and start playing the game as well. So let's talk about our speech interface and the experiments that we've done. So as we've discussed already, we have a Rugged Radios headset. We have 2 different channels. So the first channel we use to talk to people. So if I want to talk to the other team or anyone on the shore, or of course the safety boat, everyone has to have a safety boat, we use one side. If I want to start sending messages to my autonomous teammate, I go on the left side, click on the button, and start sending messages. The push-to-talk was super critical because we originally had no push-to-talk, and the noises of the environment were triggering our speech recognition. So the motor would constantly say no, you'd yell something, and then before you could say yes to acknowledge a command, the motor would say no. So you're just like yelling at the motor, so it's not really useful. So push to talk was great. And we're using the Julius speech recognition engine provided open source from a university in Japan. The way it's set up, you can put on any acoustic model that you want. We grab one from VoxForge where people read text and then talk out loud and record that, and it's constantly being updated and added to. We define a simple vocabulary set of names, which in this case include robot names, Arnold, Betty, Charlie, and team. Different commands, in this case for early experiments, included return, deploy, follow, and station. And of course you need to be able to acknowledge your commands, right? Because sometimes the speech recognition hears the wrong thing, or you say the wrong thing because you're overwhelmed and you like forget your teammate's name, or you're saying something that you shouldn't. We set that up into a grammar where you can then define how the sentence structure is structured using name and command, and of course acknowledgments. So in any kind of speech system or interface, you typically have a dialogue system. Ours is super simple. It waits for a command. When it receives a command, it'll wait for an acknowledgement from you. So at this point, it'll say something. If you say Charlie follow, and the system will ask you, did you mean Charlie follow? You can then acknowledge it. If you say no, it just cancels and goes back and waits for a command. If you say yes, then it will, of course, trigger that command, sending it off to your teammate. And, of course, tell you that the command has been sent. So here is a fantastic time. So Hugh Doherty is in the audience. Hi, Hugh. He's been great. He's been with me from the beginning. We were lucky to snag him in his gap year between high school and going to college. And originally it was just us running experiments. So here you see a great November day in 2016, right? Yeah. 2015? Yeah. Hugh's getting into the motorized kayak. He has the headset. He's putting it on. There I am in the green shirt. He's deploying. And what he's testing out right now is saying, Arnold follow. And Arnold, of course, asks, did you mean Arnold follow? And he says, yes. So in preparing this talk, I actually found myself rewatching this video over and over again, not even needing to, because it's just awesome. So the robot's trying to stay behind him over his left shoulder. Not too close, so it's difficult for him to see. He uses one of the last commands, which is Arnold return. Arnold comes back to base. So our robots are designed that if they run out of communication, they just hang out. Unfortunately, Hugh is not designed that way, so I couldn't get a hold of Hugh, and he just took off, so I had to go chase him in the boat and let him know. We've since upgraded our equipment. We have a big antenna at the pavilion. High fives are super critical for our success, and we definitely spend some long hours. That was a great day. All right, so one of the things that's super difficult with people is that they're very messy, and particularly trying to measure exactly what they're thinking and why they're doing certain things. So if we just try to measure people while they're playing the capture the flag game, which is very, very hard to figure out what's really motivating what they're doing. So we try to pare down the capture the flag game into something smaller that we can manage, and that way we can change our independent variables and try to measure dependent variables as much as possible. In this case, what we've done is take that initial human-robot system and give people a task of taking the robot to buoys on the field. So in this case, a human will go up and say, Arnold follow, then when they get to the buoy, say Arnold station, and then repeat that, trying to get the robot to the buoy as close as possible. We told the people that they were being scored by how close they can get the robot to the buoy. Here is an example of the entire experiment. So on the bottom left, you see the MOCI starting at the dock, just like you saw in the picture, with the robot behind it. You can initiate saying Arnold will follow, you say yes, and the robot will follow you to the buoys. And then you repeat that going from one buoy to the other. The order didn't matter. It was up to the participant to do whatever they wanted and use any of the commands available. So in our first iteration of the user-centered design experiments that we ran, we got a lot of feedback. Some of the very useful feedback was that actually us just watching the operators, they would be sitting in the MOCI and then doing this constantly. And then like looking over their shoulder, which is great for your abs, because I actually ended up doing that as well, but not so much if you don't know what your partner is doing. So what they requested was more feedback from the robot. So the way we handled that was we added a couple of modules on the robot, so the human could ask questions like, what's your status? The robot would give you an intelligent response saying, oh, I'm following you, or I'm stationing because you told me to. No, we don't make robots sarcastic. Sorry, we try not to. The other thing we added was that when the robot switches modes from one thing to the other, it'll actually tell you something. So what happened before initially was I would give the robot a command, I would acknowledge the command, the system would say, oh, it was sent, but then the robot would never tell you that I got the command, right? So if you erred or there was network issues, you would never know that there was a problem. So you just spend time looking over your shoulder. So as the robot switched commands, we would then add an announcement. And of course, we also did some post-mission questionnaires, NASA TLX index, and trust measures from Schaefer's metrics, and some open-ended questions, including an interview. Hugh and I went to go give a presentation on our first user-designed iteration up at Roman. That was a great time as well. And then we wanted to see what some of the other effects were. So we want to see how well our system compares to actually having a human teammate rather than just a robot teammate, right? So we augmented a really cool wooden boat with just all the sensors you needed to localize, so GPS, the Wi-Fi antenna, and a laptop. And we had the boat, in this case Hugh, travel at 1.5 meters a second, just like the robots, right? So we want to mirror the capability of the robots. And we had Hugh constrain his vocabulary and grammar to exactly what the robots would do as well, right? So we could see what were people thinking in the post-mission questionnaires. So we used the NASA TLX index. We had a 10-question robot liking, some general engagement questions, Schaefer trust scale items, and gathered some demographic information. And of course, the open-ended and interview sections are my most fun. So our participants that we gathered, we got 15 of them from campus, mean age of 29.5 years. They reported that they were comfortable on the water. That tends to happen if you're close to the sailing pavilion. People tend to be comfortable on the water. And they had a range of comfort between 2 and 6 on a 7-point Likert scale. So other results, we performed a Wilcoxon-signed rank test, trying to look at the differences in the way that the humans responded about the robot teammate versus the human teammate. And my favorite responses are highlighted here in red. And the top one would be, the question would read, led astray by unexpected changes in the environment, and then you would indicate a percentage of time, right? So in this case, for the human, the median response was 20% of the time they were led astray, which I find very entertaining. And then the robot, 40% of the time. So then we would go down to the second question is warn people of potential risks in the environment. So everyone, I guess I don't want to say that they were just thinking about Hugh in particular, but the human teammate was 70% of the time versus the robot 30% of the time. Then performs tasks better than a novice human user, and 70% versus 40. And then meets the needs of the mission, 90% versus 60%. So we presented that work at the International Conference for Social Robotics in Missouri. And of course, we still are performing some ongoing analysis. So things that I'm curious about is quantitatively, did the human do a better job at being closer to the buoy, or did the robot? And was there differences in the total distance, was time of the mission, and how many communication errors there were. And that is still ongoing. So let's talk a little bit more about what we did over the summer. And over the summer of 2016, we went ahead and did most of the game development for the Quadicus project. That required quite a bit of rules development and development of the software, right? So these modules are all added from the Moose IVP community. Things like the flag manager, so it's a virtual flag. So we were thinking about doing a flag that you can grab, but then having a robot arm attached to our surface vehicle could make things very, very messy, grabbing flags and dropping flags and doing all these different things. So a virtual flag made a lot more sense. So we have a flag manager module that tells you whether or not you successfully grabbed a flag and who has a hold of the flag at the moment. The tag manager keeps track of the location of the vehicle, what side of the field they're on, how close in proximity they are. We try to limit the range at which people can tag each other. Then a very simple autonomy was set up for novice users that can come in. If they don't want to make their own autonomy package, they can show up and use the one we have. And typically that's the one we've been working with the most. That was done by Saad Ibn Siddiq, one of the former postdocs. Then we also did an aggressive amount of red teaming, both in simulation and on the water, to make sure everything worked. So let's talk a little bit about the vanilla autonomy that we have. Right now, you can ask your robot to defend. You say, Arnold, defend, and it'll go over. And so I made an image here with a circle, and the circle goes outside of the field, but that's just for visualization. In reality, if you go outside, then you consider tag and have to go back and get yourself reset. So I just made it big so people could see it. But the robot would have a set of waypoints around the flag and simply go in a circle. And anyone who came close would just get tagged by the robot, and that was sufficient. We can also ask the robot to attack. And in attack mode, the robot treats the flags as individual waypoints. We'll go to the opposing team's flag, initiate a grab. Whether or not it gets the grab, it doesn't really pay attention to that just yet, and then comes back to the flag area in a repetitive cycle. Another behavior, and of course this is not to scale. It's okay. It did sound like one of my videos though, that's great. So of course the vehicles aren't to scale, but this is a tactic that we use quite a bit, which is cover. So you can use the robot to go in front of you and have yourself behind it. So guess who gets the tag as you go into enemy territory. We also played around quite a bit with the parameters. So letting people tag repetitively became quite a nuisance to the game. So giving them a timer so they selectively choose who to tag is much more useful. So another behavior that we implemented was follow. So in this case, the Mokai vehicle is the leader, and the robot now trails behind you at a certain angle. Really useful if you let the robot grab the flag and then you start telling it how to get away. So as you can tell, Aquaticus is a very people-intensive game. So you need a lot of people just to make it work. In particularly, on a regular day, we have a chase boat for safety, in particular keeping all of the Charles River traffic out of the way. Then we have people on the dock watching for traffic so they can communicate, tell the chase boat what's going on. Then we have people watching the robots just to make sure that they're actually functioning the way they should and haven't taken off towards Boston. And then people in the Mokais, right? People actually in the vehicles themselves. So this is our team from the summer of 2016. As you can see there, we have 6 Heron vehicles and 2 Mokais in the back. But this happened to be on a day that Hugh wasn't there. So Hugh has to get his credit, and we have his own special picture here. This is actually on a day when we got one of the robots, and he's very excited about the robot. It's pretty awesome. We did quite a bit of demos over 2016, so this was all just exercising our vanilla autonomy and our human-robot interaction improvements. So let's look at a couple of demonstrations of what we can see. Okay, great. It's really pretty. You guys get a chance to come hang out. So you can see here, that's where the sailing pavilion is. The midfield is the flag for the sailing pavilion. Here we have the buoy, the red flag right there. And you have two mokais and one vehicle going back and forth. So you'll see some interesting interactions between the vehicles. They're all trying to avoid using coal regs what the other person is doing, right? So initially you'd think sometimes a collision avoidance would be very simple just by moving out of the way, but they're trying to make sure that they follow various stand-on and give way conditions as well. So here we see people going towards the blue flag. That individual just went around the blue flag, is now coming back. In the distance, you can actually see the chase boat and some buoys we have during competitions. So while it looks kind of slow, this is real time, when you're in the Mokai, it's a lot of fun, and it's very chaotic, trying to figure out what's going on. So let's actually look at certain plays that we have. So here, in this case, we have Felix, who's on the red team, on a run for the blue flag. So you see Felix down here, and he is autonomously going for the flag while the humans are distracted at the other end of the field. He grabs the flag this way and is now taking off back towards the other flag to score a point. And then here is where a human gets involved with the robot. So I honestly have no idea what they were doing on that end of the field. But I definitely know when they make their mad dash this way, it's because someone has the flag. And it ends up being this robot right here has the flag. Now this individual right here closest to him is trying to tag, right? Tag, tag, tag. What ends up happening though is that the tag is given to the vehicle closest to you, right? So the human of the other team starts interfering with the tag process by being closer to the other person, so the tags keep hitting the person and not the vehicle with the flag, right? So those are just some fun interactions that happen while we're playing the game. All right, so let's talk about some challenges on here. All right, so there are plenty of challenges because we're on the water, right? So one of the issues we had with our motorized kayak is that we started noticing some backfiring from the motor. Then we noticed that the motor wouldn't turn on. And then I started investigating more about what's going on. So there were dirty spark plugs. And we started doing a little bit deeper analysis. And this video will give away everything. So if you can see here, water is splashing up onto the deck and then into the air intake. Over here we have the air intake for the fuel tank. As fuel gets consumed, the air is supposed to come in and equalize the pressure. So if water is getting into that air intake, then you can't equalize pressure, and possibly water is getting into the fuel. So we'll look at that one more time. So watch the air intake, and you can see water going up and into there, and then gray smoke coming out. So that's not a good sign. Oh, and for the record, I had no idea about any small engine problems until this project, so I'm learning quite a bit. But you know, we persevere through these problems, and we keep getting information so we can figure out what's going on. Here is actually a picture. We took apart the carburetor, and we find that this is fuel from the carburetor. And on the top layer, you see fuel, and then the layer underneath is a bad layer. It's water. So water with your fuel is not so good. And so what we started doing is communicating with some friends at Hui, and what they have actually done is turned their motorized kayak into an autonomous robot. So they sent it out to do monitoring in rougher waters. And they actually came up with, you can see some of these images, there's a black cover or hood to their air intake, and we are in fact in the process of putting together one of our own. I actually just left some of our interns this morning working on that. So we're hoping that'll be pretty useful. The other thing we're going to do with these MOCAIs is, if you've ever been in them, they're super, super loud. And it's difficult for the human speech recognition, but in particularly for those that live in the environment and the sailing pavilion. And so we're thinking about adding more vehicles. So I think the best approach is to turn them into electric vehicles, which is what we're doing. Unfortunately, the prototype should be ready midsummer, and then outfitting all the vehicles after some iterations will be at the end. So we're going to be working with our gas engines just a little bit more. One of the other issues we found is that the herons aren't quite consistent. So that makes a big impact. If your robots aren't consistent, it means your teammates aren't consistent. If I'm on a team that has an amazing robot, then that gives me the advantage with the team of the robots just kind of limping along, not quite going as fast. We've noticed in particular that turn radiuses are affected. And one way to deal with this is to measure exactly how they're affected and try to make all the other robots uniform if we can't fix it. Then of course, if all our vehicles are having problems, might as well include our human-robot interaction, which is using speech. So in some of our user-centered design experiments, I had, in particular, females come back super mad at me and telling me, why are you programming the robot not to listen to me? And I was like, it's totally not what I was doing on purpose. So there was a high failure rate of the Julia speech recognition engine with female voices. And so what we've done is get some of our talented undergraduate students to start looking into exactly what is it that's happening with what's going on. So what we've found is that in particular, Julius isn't doing well when the pitch gets too high. And if you get too loud, it starts cutting off the microphone, right? So if your microphone is getting clipped, then obviously you're going to have problems with distortion and everything else. So at least we've come up with guidelines that tell people if you get too excited, keep your voice kind of low. And we've also noticed that people get excited and start yelling because they think that the speech recognition engine isn't working because they're not loud enough, which in fact makes it worse. So at least we can give people that if we don't necessarily change acoustic models or start tinkering more with the engine. So here's Abby Lee. She's great. She's a freshman this year at MIT, and she was helping us since January working on this project. So she was excitedly ready to leave the lab and get out onto the water with the with the robot kayak, right? And start doing the speech test instead of doing it in the lab. And so what she was doing was going out. You can see here, there better, the motor. And just, cruising around the river, trying out different commands to see exactly when it fails, why it fails, and everything else. So one of the hard parts that I find that we're struggling with is making sure students go to class and trying to make sure that they don't come hang out with us all the time. So I'm not sure how to do that. Well, I really want them to be excited, but I definitely want them to do well in class. All right, so mind you that Abby worked with this since January, right? So she knew all of the problems with the system. So I was really surprised to see some of the results that we got from that. So here's the success, and this is a success from inside. Am I saying this right? Can people hear that? So that sounds great, right? It's very clear, no problems. Then she gets on the MOCAI. This is her first time on the MOCAI. Okay, so in the background you can hear the motor, right? So that's the problem. But then you could also hear how excited she is to be on the MOCAI. So when we came back, we were all listening to the videos, and we were like, wow, nothing worked for you on the water. It's really, really strange. And then we started listening to the videos, and she was like, yeah, I was so excited that I didn't really pay attention to my voice, and I was just talking. Yes? I'm ready.
So you're telling them to control their excitement, but in real life that's not always going to be the case. So are you doing this just because of the Julius kind of issue, and you're just trying to get around that for now, obviously, so you can focus and control?
It's more of a Band-Aid, right?
Okay, yeah.
Just so I can get things to work.
In real life that's going to be, especially.
I agree.
Yeah, okay.
Yeah, absolutely. But it was also very exciting that she's like our expert user, right? And it was like so excited that she, yeah. So let's talk about some next steps. So we had a huge month as far as getting approval. So what happens with this project is that I have to first get approval from MIT to do any human-robot interaction work. And then I have to get approval from ONR. And we just recently got that approval to do pretty much everything we asked for, which is awesome. So the first thing we asked for was, can we actually start recruiting participants to do simulation if we do so. Simulation is great because it lets you work out the kinks, but of course we prefer to be on the water doing all the experiments with the Mokais, the robots, and chase boat. So the full competition has been included. We've also added the ability to start taking physiological measurements of the people. So in particular, I want to look at the heart rate and respiration rate of the people, along with galvanic skin response to see exactly how excited everyone is. We've gotten approval to have a public data set. So what does that mean? We are going to take our data sets from what the robot is thinking, what the people are doing as far as their trajectories, video of their faces, along with what they're saying, and package that up with some analysis and make it available for people to start doing their own analysis with what they're doing. We hope that to leverage other people's expertise into the same data set. The other thing we would like to do is actually have like sports competitions. Think of like having a football game where you have announcers paying attention, different camera angles, and people talking about what's going on. We're thinking about having live stream competitions with the ability to have repetitive games. So we're hoping to recruit participants to come hang out for a week and repetitively play the game with either our vanilla software or with Autonomy that they put together. We're also including our summer interns as repeated participants so that we can report the data that they come up with. We're also looking to go to a full team size. So originally we had just a simple one human vehicle and one robot. And now we're moving towards having 2 human operated vehicles and 2 robots. Yes? Hi.
Maybe you're going to get to this in a minute, but going forward, what is your research question that you're really trying to look at when you're going to prove by the end?
Everything. So give me 2 more slides and we'll talk a little bit more. So one of the research questions we're interested in is looking at team structure, right? So we want to know exactly which structure is more useful in this kind of environment. Do we want it to have flat where everyone is equal participants? Maybe that's like a Freudian slip. Equal participants, or do you want a centralized commander? Do we have 2 sub-commanders, a human and a robot together doing everything? Or do we want to have the robots in charge? Because as roboticists, that's not really our favorite. But we're curious to see what people will respond to. The other thing I'm hoping to look at is measure cognitive load through using the physiological measurements, right? So through heart rate, through the galvanic skin response. And if we can measure that, then can we also have the robot autonomy respond to an operator who's under a severe load, right? So if my robot can change the way it's communicating to me or the way it's being controlled, that makes a big difference. So our post-mission analysis tools, we need to certainly incorporate the speech and the video that we're gathering from the participants. As up until now, we've been using GoPro and some very different tools, but we really want to integrate it into our software suite so that at the end of the mission, I can just put everything up and then be able to click on a user, look at their video, and listen to exactly what they're doing throughout the experiment to see exactly what was going on. So your question about what it is that we were looking to measure originally with our proposal, and that's trust. So we're looking at exactly what is it we can do, how do we measure the trust between the humans and the robots? And that happens originally by the people who are designing the robot. Are they thinking about trust when they're designing their autonomy? And we're also trying to measure using Schaefer's trust questions. We're looking at ways that throughout the entire game are atomic decisions in how you use the robot signs of how you trust a robot. So if you trust them in scenarios where there's more risk, as in do you use them in more risky situations, then that seems like a good measure of trust there. And also, are there new measures of trust that we probably can bring out of the data? This is, again, a big program with a lot of people that are required. And so We went through, Hugh, of course, gets credit, right, for setting up the high school internship program. Hugh went out to high schools and tried to recruit people from robotics teams that are already in motion and asked them to apply to our program. We had a little mini quiz so you could self-select whether or not you actually apply. Then we had 24 applicants, 12 came in to do the interview. We put them, because we're so much time on the water, we put them through a boat test. We give them a command line test because that's how we interface with our robots. We give them a C++ quiz, mainly because we're programmers, but also because eventually they start programming as the summer goes on. And most important to me is that they get along with Hugh, because he's the person running a lot of their show. We have 4 hires for the high school program and about 6 undergraduate students coming to work with us over the summer to help with all the different things. No man is an island, and so I have a lot of people that help me get along the way here. Hugh on the right, of course, getting credit, and then everyone else. If I miss someone, I apologize. And I'm open for questions.
So when you're evaluating how much the operators trust the robots, how do you want to separate out the question of whether or not I trust the robot to do what I asked from the complications of the Band-Aid, or the fact that it might be that I trust the robot to do what I want it to do, but I don't trust that it will understand what I'm asking it to do just because of the limitations of the
That's a great question, right? That's a great question. So unfortunately, in the questions we're asking, right, like on the Likert scale questions, that doesn't tease any of that out, right? A lot of the times we end up asking, so we'll see something happen on the field, and then we'll ask in the interview different questions about what were they thinking, what's going on. So unfortunately, we don't have anything that particularly specifies that at the moment. But that's a great question. So yeah, the technology of whether it understands me versus is it actually capable, once it understands me, it can actually do what it's doing. Yeah.
Does anybody else have a question?
Did you want the box?
So I guess I understand what you're measuring and so on, and I'm just trying to understand what your key research question is. Like, do you have a thought that if that somehow this workload and the trust measurement combines in a certain way? I'm trying to understand what your research question is.
So we're trying, so at least our hypothesis is that the best performing team will have a robot that's high functioning, low on operator cognitive load to interact, and of course, high trust between everyone. So we're trying to show that all 3 of those pertain to a team that does better than the others, which requires a lot of games and a lot of different teams to go through.
Do you have any kind of manipulation at all? Are you doing any manipulation in between independent variables and then measuring these? And it sounds like you're interested in the overall correlation
right.
that
So,
define.
so that's
but
right.
I think to the research question, like, are you trying to look at any differences?
So like what I showed initially, right? So the game has so many different things happening. How are we going to constrain so we can just change the IVs and look at the DBs, right? That's really what it's all about. What I think the best answer to this is, and Paul and I have been mulling over this quite a bit, is maybe trimming down the game more to like a half-court scenario, where I can then really just look at the defense versus offense and manipulate exactly, okay, am I manipulating how the robot talks to me, or am I manipulating something, right, about here, yeah. But it is important, right, because then I can make stronger statements about what we're changing to what we're observing. If we just have a 10-minute game and I change something and that what I changed never comes up in that 10 minutes, then it's kind of hard to really talk about. So hopefully I'm addressing what you were saying. Yeah, but it's multifaceted, and there's like a huge state space of what's going on. Even just location-wise, if you're interested in how things interact like in geometric perspective, getting that to happen with a live game with many, in this case, going to be 4 participants, it's going to be really hard to constrain to make that actually happen.
So I don't know what your analysis is saying. Good data visualization techniques might kind of shed some light on that larger pattern
Yeah.
that you might want to, that it sounds like you're mostly interested in, kind of the pattern of the data and the things that are interacting versus, again, I don't know what your analysis
Well,
is.
so what's great about coming to talk right here is to get a chance to meet other people and talk to you about this eventually, right? Maybe after your presentation. So yeah, no, we're always looking for different ways to analyze the data. And also, that's another reason why putting a public data set is so great for us, right? So we want to look at like certain things. I'm really excited about the physiological measure thing. I really want to see if someone's heart rate's going crazy, if the robot can help.
We'll talk offline, but I do know some people at Pacific National Northwest Lab
great.
that data visualization
Oh,
would
great.
really help with this.
Yeah, that's awesome. That's awesome. Yeah.
So there's a question online. What distinguishes a human-robot team from a semi-autonomous system?
Let me restate the question because I didn't get it. What differentiates a human-robot team from a semi-autonomous system? As in like a control theoretic perspective?
I don't know.
Okay.
Or are they the same?
Well, so what makes something semi-autonomous? That like, it does something by itself every once in a while and someone says something to make it happen? Maybe some more clarification would be helpful.
If you want to ask your, articulate that question more on Skype, and we can try and answer that better.
Yeah, sometimes I wonder if questions are philosophical and not really have a solid answer.
Autonomous with human oversight.
Yes. Right. So okay. So here are different ideas. Okay. So that's a good question. Good clarification. So there's many levels that we're actually thinking about. So the first one would be direct control, where the human tells the robot to do every little thing. And then we go to another example where the robot comes to you with a plan and says, what do you think about me doing this? And you say, it sounds great. Or you modify the plan and move on. Versus what I think will be really helpful when people are under stress is the robot just does it, right? Comes up with a plan, does it, and then if you then eventually go back and check and you're like, oh, that was awful, let's change that plan, then that's the different levels of autonomy that we're thinking of. So I think yes is the answer.
If I could add to that, there's these levels of autonomy, right? So there's known levels of autonomy that are kind of out there in the literature. And I think with this whole push, and I see you're pulling from DARPA and ONR, and obviously they've got their guidance, right, in former Air Force. So again, what we're trying to get through, at least with that kind of high-level vision on what we mean by human-machine teaming, or what the DoD and the third offset and all that I'll get to means by human-machine teaming, is a fundamental different, where that truly is an autonomous capability that can act on its own and respond, not just automation, right, with certain levels of autonomy that are controlled. So the
thing. So what's interesting, what you just said was that you said automation. And to me, automation is something that's not very flexible and brittle, right? Automation is like, I think of like something cutting something on a repetitive basis, versus autonomy is something new has happened and I have at least a plan to handle it and adapt to what's going on. Yeah.
that's the goal, at least in the guidance that I'm sure you're
Yeah. Yeah, no, that's great. That's great.
Are there any more questions? Well, so thank you very much, Misha.
Of course, thank
And
you.
a number of us were actually played Capture the Flag on the water last year, and it was a lot of fun. It's more fun than it looks. I mean, it looks fun, but it's like really fun, and it's also really hard. It's harder than it looks too. So there is another thing that I'm going to do right now to really embarrass Misha.
Oh, man.
It's his birthday.
Awesome.
So happy birthday to you.
That's
Happy
great. That's great.
birthday to you. Happy birthday, dear Misha. Happy birthday to you.
Thank you. Thank you.
very
I
much.
appreciate that. Awesome.
Thank you. So, do you want to say a couple quick words, or go right to Charlene? All right. Our next speaker is getting set up here, Charlene Stokes, who joined MITRE like 2 weeks ago from...
This is 3 weeks now.
3 weeks, going on 3 weeks, from AFRL.
All right, thank you.
All
All
right.
right, okay, hopefully everybody out there in the cyber world can hear me. I have to say, as excited as I am to do the capture the flag, Misha, I think I will fail miserably because, as you will learn as I talk, I get very excited and I am very loud. So yeah, it's trying to control for somebody like me is going to be a challenge. Okay, so let me make sure this is working. I'm a big preference for this thing. I move around a lot. So anyway, I definitely wanted to say thank you to John for organizing this and coming up with this idea to kind of bring these worlds together. And also a huge thanks to Marissa, who I know was a huge help to you, John, and especially because you're doing that on your personal time. So thank you very much. It's very much appreciated. Other thanks, which it seems like they left. Oh, no, Joyce is there. Huge thanks to Joyce and Tom, of course, for the tremendous support. Joyce, just again, just like Marissa, kind of, oh, we'll just get you snacks. We got that covered. No worries. So thank you very much for that. And again, really, for those of you that might be residents here, MassRobotics has been a tremendous resource, and I'm really, really so glad we decided to come here. This was a decision I made back, again, 3 weeks now at MITRE, formerly with Air Force Research Labs, but I've been with MassRobotics, again, kind of tracking them, and Tom was really great for about a year now, really tracking them, waiting for them to get this space, and they finally got it, and as soon as they did, we made sure we were some of their first residents, and it has been paying dividends ever since. Again, the tremendous support, the tremendous connections, really great opportunity. So anybody that is interested in looking for any kind of residency or all the things that Joyce mentioned, please definitely follow up with them. Highly recommend it. Okay, so unlike Misha, I did also get my bachelor's degree in psychology, and I decided to stick with it, but you can still play with robots, okay? So I just come at it from a very different perspective. If you want to read that, what I always say a quote, but I guess it's more a motto that Marissa and I kind of came up with, developing and managing the unique relationships for future quantified warriors and their machine partners. And if you understand that, where I'm saying the human-machine teams, but the social frontier, and managing those unique relationships. So that's what we're trying to tackle. We're trying to understand it not just from the design perspective. We have all these great minds here, right, that can understand and kind of feed into the design perspective. But we're coming at it from a different angle. And the reason I'm coming at it from that different angle is because my training, again, sticking with the psychology, is actually I got my PhD in industrial organizational psychology. And what does that mean for some of you folks that don't know? I did have a dual program. I did human factors psychology and industrial organizational psychology. But with my focus in the IO world, it's very much on teams and team effectiveness and all this world. So as you might imagine, when this whole notion of human-machine teams came around, I was like, I happen to know a lot about teams. So it very much intrigued me. And again, we really want to bring it back to what we can do for managing that relationship, not just on the technology side, but on the human side as well. And so that's the question that we're trying to ask. The work you're going to be seeing here today, again, I'm at MITRE, been MITRE for 3 weeks, but again, much of the work has been a research program because I have been with AFRL for 12 years. So a lot of that's thanks to them and support by them, but it's really these folks that you see here that have really done the hard work. Very much a team person myself, outside of just trying to understand how they function. I try to live that. So again, Monica and Marissa, I can't thank you guys enough for everything that you have done. And then we've got some great support from Accreta. Again, these were not just my contractors, so I wasn't just paying them to do work for me. But we had Accreta with them, and they were a tremendous team and really gave their all these folks you see here listed on the Lockheed side. And then some, when we were at Yale for the last 5 years, some great support we had there. So again, thanks to them for the work you're going to see today especially. So some of you out in MITRE world, I hope there's a lot of folks tuning in hopefully. I'm learning that that's how everybody seems to attend meetings at MITRE. They kind of do this virtually, so hopefully there's a lot there. Most of you probably know about the third offset strategy, but for those few folks that are here, either from MassRobotics or MIT, although you guys are funded by DARPA and ONR, so you probably know this too. These third offset strategies are huge. Obviously, there's only been 3 in our entire nation's history. First one, nuclear deterrence. As you might imagine, that's had a tremendous impact on our world, not just our nation, but our world. Second one, we can summarize it as technology superiority, right? So what did that mean? How did that affect our world? So for example, it's not just defense, but it trickles out to the defense funding world, which trickles out to the DARPAs, trickles out to the universities, and then there's all this influence that goes on. Essentially, we'll just boil this one down to one of the big ones that came around from the second offset was GPS, right? DARPA trickling down and funding and that exploding. And we see things like the autonomous car kind of explosion, which again came pretty much from one of DARPA's challenges earlier. So this third offset's coming along, right? I get excited because it kind of lined up with the work I've been doing in trust and autonomous systems for 12 years, so that was great for me. But what I noticed right away is some of the pillars that work announced were human-machine collaboration, unmanned-manned combat teaming, as if those are easy things to do. Collaboration and teaming are incredibly social aspects, and then that component of it is completely being neglected. Not saying that it's not important to create the capability and the technology itself, but we want to understand the other side as well. And again, that's what we hope to be able to bring to the table, to work with the folks that are developing the great capabilities, and that's one reason we're here at MassRobotics. Again, to work with those great technologies, but again, we're kind of coming in and trying to ask some of those, what can we do on the human side to improve this true teaming or true collaboration? So again, it requires social emotional skills, and what I present in our studies today, you'll see a little bit more why I highlight so much the social emotional part of it. Not just because I'm a very emotional person and really excited, but obviously I exist, right? Someone like me exists out there, and we have to understand how we're interacting, right? So our objective, just in general, is really trying to understand those social cognitive underpinnings that are existing, because again, we are social emotional beings. We use emotion to inform our decision making. We're processing it on an emotional level every second, every day of our interaction. There's a reason we have those emotions, whether it be a steady affect, whether it be high emotions, and we can get into emotion theory offline if you want. But again, there's a purpose, right? It's there, it has survived, and it informs our decision making, whether we want it to sometimes or not. So that's what I want to understand in this human-machine teaming space. And I specifically want to pull in, again, my background in IO psychology, which I did focus on motivation and training theory, so I very much want to try to pull that into this space. How do we motivate? How do we train the war fighters for me, the users for other people? How do we start thinking about how these people are engaging with these systems from the beginning, and what can we do to get them ready for that? What can we do to get them potentially more accepting, more trusting, less trusting, depending on what we want there? On the commercial side, for the MassRobotics residents here, that usually gets bared out in the markets, right? Some marketing literature and some marketing science goes out there and does a lot of their own physio work. You should see the P&G lab that they have set up with eye tracking and everything, trying to understand those exact things. Again, what are those social cues? What emotions? What's leading if you're placing it here? If it's colored this way? Again, instead of waiting for that on the defense side, we have to understand some of those, because it comes down to life or death. So again, the largely unconscious social affective cues are what we're looking at, and we do certainly see that as a wide and critical gap. Again, in 12 years of doing trust and autonomy research, I've recognized that and have been studying the relationship between trust and affect, or trust and emotion, and that's just going to become more and more important, not only obviously because of third offset and all the trickle-down effect of the powerhouse of government funding that's going to influence, but just everything that's happening in the commercial sector with Alexa, for example. The Amazon Echo, I have one of those in my house, and as a mother of a 4- and 6-year-old, they are interacting with Alexa just like she's, again, really like she's part of the family. They'll ask her questions, they'll do all kinds of stuff, right? And how's that interaction space happening, right? They're just growing up that way. So how is that influencing us as we move forward? So here's, again, to your point, Misha, definitely on the physiological side, right? It's important for 2 reasons. It's key for that perceptual system of the machine, right? That machine needs that data from the human. If it's going to be a teammate, it needs to know something about its human partner. What's the best way to truly know that? Because I'm going to pick up so many signals from you, from Marissa, I'll say from, again, when I'm processing this, that aren't just everything she's telling me. And maybe she's not telling me some things, or maybe she's lying to, oh no, I'm okay today, whatever, right? But I know, right? So again, the physiological side, all the biometrics, right? That's going to be a really, really important piece for that perceptual system, for the machine to have its perceptual system. What we're interested in is simulating that intelligent partner, right? Again, because we see AI going that way, for an intelligent machine partner to have that, we see it going that way, that all this data is going to be collected, quantified warrior, right? Quantified self, quantified warrior for us. But how are users feeling and responding to that much more intimate coupling with these systems, right? I think that's an important question, and that's easily being glossed over it. So again, that's something that we're trying to tackle and trying to understand it from that perspective. So I know you probably cannot see this at all, but there's really two main things to highlight, really just the yellow portions here, right? So this is some great work that we've published and put out there, because again, as a fundamental scientist and trying to understand the theory and build up the theory, we've developed a conceptual framework for how we want to understand this human-machine social systems that we believe they are. And the blue, and I don't know if this works. Oh no, it doesn't work on that. In the blue side, we've got technical skills on the machine and the human side, and individual characteristics on the machine and the human side. Again, these are important, but where we're focusing in our research program, or we have been, and hope to continue to do so, is on the team process skills. Again, how do we get both sides, right? Not just the capability of the system, the design information for the system itself, but how do we get the user ready for that? So what it lists out there in team process skills, some variables we're interested in: communication, collaboration, cohesion, rapport, and team management. And how do we plan to tackle those? That's what you see down here in this yellow box. Step one, human-machine selection and training. And again, pulling in my IO background there, how do we select for and train for people that are optimally going to work with these systems a little bit better? And then the climate management, the continuous kind of, and this again goes right back to the physiological sensors. If a machine partner, like in the loyal wingman, there's some sensing happening that they're stressed, how do we augment that behavior? How did the machine step in at that moment, just like you'd expect a real human teammate to do? So emotion management skill training. That's another piece, again, on Marissa and I met Marissa. She started working on our team at the Yale Center for Emotional Intelligence, so we're both very steeped in emotion theory and understanding the importance of that, and really finding how critical that emotion management is in high stress scenarios. And as you might imagine, in the military, there are a lot of high stress scenarios. So we really see that as one of the key things that we can focus on. Okay, so what I'm going to do now is take you through two studies. The first one, study one here, that occurred in the lab when we were at Yale. Again, university students. We had some great results. As I stepped through this, though, just to highlight, there's a reason I wanted to pull out of the lab and come in to start using with more real-world technologies and kind of what's out there. Again, what are we seeing in the lab? Is that generalizing out to the real world and get closer to those end users? So here what we have is a basic, again, here's my manipulation, here's what I focused on, is how we introduce the system. So again, how we focus on the training, if you will, but including in the training is just some basic framing, some basic social framing of how we're even introducing those systems, right? So here we said, we framed it as, it's in the experiment condition, as an empathetic partner focus. They go through some various team building skills, and again, it's really emphasizing that social fabric that underlies most interactions for us as humans, whether we like to admit it or not. Control condition, tool focus, yoke control task. Again, this is typically how things are introduced, right? Here's some great decision aid system, and it's going to help you in your task, and here's how it works, and that's about where it ends. And then it gets put on the shelf soon after, at least. That's what we often say. So again, we were just really basic kind of trying to highlight that social focus and just some simple framing manipulation. Everything that happened, as you can see there, same ISR, and for those that don't know, ISR is my former group in intelligence, surveillance, reconnaissance, so the analysts of the world, right? So what are the analysts doing? This was the participant in this was pretending to be an analyst that had to rate various threats, and KEP, either the computer empathetic partner or the computer enhanced program, would aid them in that and make various recommendations. So here are some of our self-report measures. We do have some physiological measures as well. We had eye tracking, EEG, and EDA, but GSR, same thing. We still need to analyze some of that data, so I like your idea of kind of opening it up and putting it out there for some folks to look at the physio data. So one of the things I found really hard, and I don't know if Misha, if you've come up against this, but again, when I kind of got into this world, I was so excited of this whole sense, assess, augment loop that we call it anyway, and at the Air Force, where you want to sense this, you want to assess what does it really mean, and then augment that behavior in real time, right? But to get from that sense, we can collect all this great data, but to that assess, what does that data mean? Am I really stressed? That's a lot of noise, and that's right now happens with so much post-processing. I keep trying to convince DARPA to take this challenge on because we need to close that loop in real time, and so far nobody's really doing it. So anyway, we still have to rely on our self-report measures and some behavioral measures. So here are our main ones, and again, I know you probably can't see some of those, but we look at trust propensity, and I do very much kind of to clarify my kind of theory of trust. I do define trust as an acceptance of vulnerability. It's an attitude versus trustworthiness, which is maybe how I feel of people out there. I'll judge your trustworthiness by, there's various models, ability, benevolence, integrity, what have you. Again, that's different than my trust, my ultimate judgment of trust. And then my trust propensity, more dispositional, right? More my personality, what am I bringing in that's kind of flavoring that. So those three main constructs, right, are areas how I kind of view trust, which is different than reliance. And you'll see in a moment in our results why that's so important. So that's what you see right there. Some of our examples of trust. Physiological reliance was the different score based on agreement with KEP's rankings, right? So did you follow up with what KEP was ultimately recommending you to do, or did you not? Coping. How able are you to handle the demands of this task? Now note, this asks nothing about KEP. It just asks about the task at hand that you're performing. And then the other one, again, was created, it was very much exploratory for what we were doing here. Again, going back to that intimate coupling that we're seeing on the horizon of we're all going to be hooked up, especially with pilots. I know that that's the way they're going, is with the loyal wingman especially, is to hook them up and get all this great human data, as they call it, off of them. Well, how do we feel about that? How is that changing that dynamic, that interaction in ways that we might not even be aware of? And before I move on to, I like this. I know what's coming up now. The reason I say, and I really want to emphasize that what we aren't aware of is because this great series of work by Clifford Nass, who unfortunately passed away right when we got on a program to be able to work with him at NSF. He unfortunately passed away, but his work really did inspire me, and it was just a series of work showing, it was the 90s even, 90s into the early 2000s. If you put one example, again, there was tremendous examples, tons of studies. If you put a colored armband on and then you color a desktop computer with a matching color or a disparate color, how they performed with that, how they relied on that, and playing some basic computer-based tasks, all these tremendous variables were impacted just simply because of that minor social cue. Okay, so again, the interesting thing though about that is when he asked them in the exit interviews, would you treat this system any differently for X, Y, or Z? No, of course not. No, never would. But yet they did, right? So what we acknowledge and what we think we're going to do you trust would you yell at your iPod or iPod, do those exist anymore? iPhone or what have you. Again, what we consciously say, we don't think but we will do, and we don't realize that because, again, it's that social cueing. We are social emotional beings. That's getting cued. It's informing our reactions, whether we realize it or not. So here, some of the stress and the coping ability in particular, really interesting results. Again, for this pretty minor study, I think we had 43 participants. Their perceived ability to cope with the stress of the task at hand was higher in that teammate control group, just because we said, KEP is your computer empathetic partner, went through some social kind of dialogue, and again had that cued, that social kind of context for them. They already perceived they could cope with that task that they were doing, that ISR threat rank task better than in the control group when we said, here, KEP's going to help you out with this task, and the ratings that KEP would give were the exact same across these conditions, and it was between subjects. Here's the really interesting one, and I've been kind of saying this in a lot of the trust and community for a while, and the trust and autonomy community in particular pretty much, remember how I said there's this distinction between trust and trustworthiness? They kind of just assume that trustworthiness is trust. Okay, can I predict? Is it reliable? Again, check all these boxes that are really trustworthiness. But then they assess it that way, and they don't come back then and see if my attitude, right, my perception is the same. And for a quick example for why it might not be, right, maybe I don't trust you, but my workload is so off the charts that I'm just going to have to rely on you anyway, right? But here, what I find fascinating about these results, what you see there with the nice slope is the experiment condition. So we presented it as KEP as a teammate. And then on the straight line is the control group where we presented it as a tool. So what we see happening here is that nice linear relationship that we assume is the case, right? That if I say I trust, then I also rely. We're not seeing that in the tool condition, and that speaks to some of the conflicting results we've seen in the trust and autonomy literature, where sometimes they're relying, sometimes they're not. And what's the difference here? And that's why I get excited about this one, because it's cueing that social fabric, right? Trust is a social variable. Trust is something that we do as social beings evolving and learning what we can trust and what we can't in those social dynamics. So when that social underlying fabric gets cued in people, then that's going to bring that dynamic a little bit closer. And so that's what we see here. And again, this was exploratory, but really even with these very basic questions that we developed for this study, we already saw a significant difference in how they perceived that the sensors enabled KEP to understand, help, and support them more, all because of what we said, that how we introduced that system versus just giving them the system, showing them how it worked. So we wanted to move on to study 2. Those were lab students, Yale students at that, so we can't really generalize too far beyond that group, right? So we wanted to see, how does this happen in the real world? That's one of the things I'm always trying to push for is get out there in the field and try to understand what is this going to generalize out there. So we were very fortunate. The Air Force has this annual exercise called Tech Warrior, where it's a 10-day exercise, and they bring folks in, and they have to live out there. They're in these tents, and it sets up this base defense scenario at this great area called Calamityville, which I know, it's crashed planes, they blow things up, they flood things. It's really great. It's for also rescue training and all kinds of, not just military training, but all kinds of folks get sent out there to this area to receive training on disaster areas. So that's why it's called Calamityville. So anyway, they do this every year, and I was like, oh, I want to kind of do a study. They're like, what? What's a study? I was like, no, I'm not just testing technologies. I have an empirical question that I want to ask on these technologies that some of you are using and some potential future technologies. So what this PED is more the ISR world, more the analyst world here again. So processing, exploitation, and dissemination just means processing a lot of data, coming in, turning it into information to get it out to the boots on the ground, right? So what you might imagine an analyst does, collect all this data, and they have to send it out to the people in the field for them to make decisions or to inform them. So again, that's a typical scenario that happens at this Tech Warrior every year. Again, it's a base defense scenario. There's a PED cell, the analyst kind of sitting in a room, collecting all this visual information from this year. They did have drones flying, and they had lots of other sensors happening. The analysts have to collect that information and then send it out to the guys with machine guns out there, but of course they didn't really fire. But it's still a pretty neat scenario. That was the picture that you saw actually in the first one with us with the tanks in the middle. So in the PED cell, typically it's 5 people in a PED cell, right? 5 analysts. That's a lot of people having to process a lot of information. Ideally, when they become expert enough, they can reduce it down to 2, but those have to be very experienced analysts before you can have 2, an eyes-on and then a screener products person. The eyes-on is literally in this full motion video case staring at video constantly. Eyes-on meaning they cannot take their eyes off, and they just sit there and stare at it. Very fatiguing, as you might imagine. Very boring, which has its own thing on the physiological side. And then they kind of shout things out to the screener and products person is really two jobs combined into one, create the product and get it out to the field. So ideally, again, to get to that expert level, it takes a while. What we wanted to say is, okay, there's another lab at Air Force that's developing this advanced sensor system for SAR data, synthetic aperture radar data, which can collect just a massive amount of data. And just all of a sudden, and again, he's developing this great technology and where it can then give it to the analyst and say, oh yeah, this is a potential threat. This vehicle is acting suspicious and circle it as a potential threat. All that's automated, right? But how, my question was when he showed us this is, how is the analyst going to respond to that particular system, right? But again, the ideal is it can eventually reduce a 5-person PED down to a 2-person PED and have those people performing at that level before they have 10 years or 5 years of experience in, whatever it is to get them there. So again, that was my basic question. Or that was the technology's basic assumption is that's what's going to happen. My basic research question here is how's it going to differ when we introduce that great system that's being developed, right? So we simulated this system and we put on a social kind of fabric to it again. And we either had it as a tool condition with just a technical focus, or again, similar to extending the lab studies, we had it where there were some social emotional cues to foster team dynamics. We went through the whole sense assess augment loop again, sensing we've got the physiological sensors, self-report, similar measures, behavioral and task, again, assess what are those constructs actually mean, what are we getting from that, and then augment. In this, we were very much interested in how we actually eventually get to emotion and stress management, trust repair, if we sense the trust is fluctuating. And this one, what you see highlighted here in red was the only thing we were able to actually do in this study. Engagement management, because we did have, oh, and I'm blanking on it, Marissa, do you remember the Connect sensor, where we and some great colleagues from Yale have developed an algorithm that can sense engagement depending on your body posture and what you're doing. Attention management and task augmentation. And then some of our outcome measures, again, the rapport, communication, those team dynamics again, trust and performance. Performance actually in this as well, we are not able to capture. Okay, so the participants, what you see here are the two actual analysts. These are experienced NASIC analysts right there, NASIC being our intelligence side. And what you see in the middle, which I know is hard to see, this is actually a virtual avatar, right? So a virtual analyst, Sergeant Rivers, those participants that again are experienced SMEs or subject matter experts, they are analysts, that they do this job every day. They come in there and they're told that it's set up as if they're going to have this, we're testing out this technology of the future, you know, it's in beta version, and you guys are going to have this machine partner that's going to help you out. And again, how we introduce it as more of a teammate versus more of just a standard tool. That's our manipulation in this condition. So because that technology doesn't really exist, we do a Wizard of Oz study to, again, simulate it. And by the way, the technology that SAR data doesn't have this virtual avatar, that doesn't have the avatar face. That's what we were overlaying with that question is, does this matter, right? Does this matter if we introduce it with some kind of social effect, which a face itself is cueing some social factors there. So again, we can't actually do that right now. That doesn't exist. So we did a Wizard of Oz study, and literally like Wizard of Oz, this other very experienced analyst, this was Sergeant Lawton, was sitting behind a curtain, just like Wizard of Oz. And what you see there on like the right side of the screen is the facial capture system that we used. So that way everything that's being recorded is being spit right back out in real time to the analysts on the other side. And they can't hear him. They don't know that he's back there. One of the really great things about this, this software is that it allows us in the tool condition to mute, right? So even though he was following a pretty good script, his natural facial, because he is, again, social emotional himself, right? His natural features might fluctuate in the control condition where we didn't want that. So you were in that software, you're actually able to dial it down. So we had a really tight control there, which was great. One of the great things, again, that because he is an expert analyst and he knows what he's doing here, he could add that he gave that kind of meta-awareness of overall mission, which again, a real human couldn't do, but he was looking at all these things and he knew what was going to happen. Again, a real analyst wouldn't have that, but you might imagine that, again, that advanced autonomous system of the future that's going to be aiding analysts in crunching all this massive amounts of SAR data, for example, or who knows what other data, right, might have that tremendous meta-awareness, and they need, that system somehow needs to get it to those analysts. So here are the results. Again, these are just our self-report results. We did a sign test as well. And again, we've got all this great physio data that we just need somebody to analyze, hopefully Monica. So anyway, what we see yet again in real analysts, right? Experienced people out there, not just university students, real analysts doing a job that they do every day, something very similar to their job, I should say. It was an exercise. We see yet again that those team process factors were higher: collaboration, team perception, rapport, communication, trust and trustworthiness also higher. Benevolence and ability being our trustworthiness measures there. And then here we see again, so again, at least some reverse direction, which no acquiescence, right? So we're seeing some good results there. That they perceive that the stress with the task at hand, again, not anything related to Sergeant Rivers, as we called him, but the stress was lower, all because how we introduced that technology and what we had them engage in that pre-task phase, right? Not just the task of the training of how you perform the task, hit X, hit Y, what have you, but again, how we're introducing them. Are we introducing them as our teammates? Because teammates means something, and it means something very social. Again, we've got all this other great data that we hope to be able to analyze and find out more, and actually both the lab and the field study. So in conclusion, I think I probably did pretty good on time. We're really trying to get at that foundational scientific understanding and really generate some empirical evidence here of both the benefits but also the risks of the social cueing, right? Because we are developing these systems are going out there, but we're not always asking, is this good, is this bad? If it's bad, how do we mitigate that? If it's good, and if it's maybe a way that we can enhance collaboration and teaming with these systems without this tremendous cognitive, burdensome display where you have this and that going on. Maybe if I just cue you as a partner and then you're going to interact with it. Again, that's a much more easier, unconscious way to get into, improve that interaction, improve that performance without it always having to be on the system and some kind of design aspect on the system. So again, just really focusing on those non-technical skills, selection training, and again, that emotional management, social emotional management throughout, and really trying to understand the relationships of the future. And that is it. Thank you very much. Any questions? I'm going to get my water.
All right, so you talked right at the end about potential, I guess, downsides to a social system. Have you done a study, or are you thinking about a study where you have a social versus a tool introduction to your system, and then you have it give them wrong information? So can it lead someone astray where it wouldn't otherwise if the users feel like this is a person?
Oh, wait, I'm sorry. Say that again. I thought you were on the reliance of it, essentially?
Right.
The
Does it
reliability
cause
of
you to over-rely?
Yeah, so that's a pretty common thing in the trust and autonomy literature, where they manipulate the reliability of the system, right? Because we kind of call that trust calibration, right? So nice linear relationship assumed, right? Do I trust, do I over-trust it, do I under-trust it, right? If it's performing adequately and as it should, it's reliable. They usually manipulate reliability for this. Then I should trust it. But sometimes we call like complacency, right? It's like, I don't really feel like doing anything or what have you, or I'm just bored, so I'm just going to be complacent about it and rely on it. So yeah, there's a definite relationship that's all optimal there, and people have manipulated that, we haven't ourselves, but eventually that would be something to do. And if we don't do it, if somebody else would want to take that on to kind of investigate that in this particular realm would be great, because that's an important question.
Representative of the general population. In the second study, you put, I would like to know, how do you realize that there's a difference between sexes, men and women?
No, so we do have that, but it's a pretty small sample size. So in the survey data itself, we can't analyze, but there was a female analyst that we had on there.
Okay.
But hopefully in the behavioral data, we've got video, we've got speech patterns, we've got all of that. And again, if we can get that data analyzed, that might be something we can touch on, but we'd need a much
Yeah.
larger sample size.
Because
to be able to
probably
look
will
at
be
that.
different.
I'm
think
sorry?
so. Probably will be different between,
Yeah.
you know.
Do you have any, Marissa, from the Yale studies, do you have any anecdotal thoughts of the exit interviews on the male-female differences? Yeah, but that's absolutely an important question, but again, just not something we were specifically looking at here.
Thank you.
Thank you.
Anyone else?
All right, well, thank you. Anybody out in MITRE world, if you're still on, or everybody's probably gone?
Are there any
now? I don't
questions
know.
online? No?
Okay, thank
All
you.
right, well, thank you very much, Charlene. And thank you, Misha, as well. Those were great talks. And thank you, Joyce, for introduction. And and thank you, MassRobotics. We're very happy to be part of this community. And we look forward to further engagements like this. Thank you. Did you want to? All right. And Russ Graves is going to say something.
I do just want to also thank Russ. I didn't thank him in the beginning, but we wouldn't still be at MassRobotics if it wasn't for him.
So MITRE's very pleased to try to bring speakers in and also be able to get some speakers from down here in Boston and feed that back to our corporate offices down in McLean, Virginia, as well out as Bedford, Mass. So it's been great. Thank you, Charlene, for that. We're very pleased that we're able to engage here with MassRobotics. MITRE, if you're not familiar with us, we're a non-for-profit. We manage federally funded research and development centers with the federal government. We support only the federal government and don't compete with industry. So a lot of our research, we have opportunities to partner and collaborate. And so this is a great venue to meet some of the organizations and startups and companies that are involved with robotics, and then be able to bring complementary research that we're doing or sponsor problems down to find those innovative solutions. And that's been one of our biggest efforts over the last few years, is to look at that consumer-driven innovations that are occurring and finding ways in which to bridge those into the federal government by either helping the startups or non-traditional companies that don't work with the federal government understand those hard problems, and then find ways to get them into the right programs and fielded within the government. So the more we can have some of our folks come and talk about those government challenges and areas where we could collaborate is a great opportunity for us. And the more we can hear about what's going on in the research community, at academia, as well as the startup companies and the technology that you have, helps us find ways in which we can either partner on that and collaborate, or bring that capability right into the federal government. So thanks for having us here, Tom and Joyce, and we look forward to doing it again in the future. Thanks, everyone.